The quotidian life depends on complex networks of communication and mass collection of data and information. From government intelligence to trivial online payments, they all require to be secured. However, with recent developments in quantum computing, the stern encryptions that secure our world become fragile, all possible due to what a brilliant mind once called real black magic calculus, Albert Einstein.
A classical bit is essentially an on and off switch. Punch cards, transistors, even our smartphones all function the same way.
Qubits, however, exploit the superpositions of quantum states. These are simply linear combinations of the computational basis states 0 and 1, where the coefficients are complex numbers. The probabilities are the squared lengths of the coefficients, and their sum always adds up to 1.
But the qubit collapses to either 0 or 1 at the moment of measurement. Thus the challenge is to isolate the system against anything that can collapse the wave function in order to maintain the delicate superposition that allows performing many different simultaneous calculations. An important example of cryptography is the Diffie-Hellman key exchange.
Eileen and Björn want to privately chat with each other. They all have access to the yellow blocks. The two each think of a secret color that eavesdropping Dolly does not know. They combine the yellow blocks with their respective secret blocks and obtain lighter blocks which they then share publicly. Eileen gets Björn's, Björn gets Eileen's, and Dolly gets both. Eileen and Björn combine it with their respective secret blocks to produce an identical violet key that they both use to open the private chat.
Dolly cannot spy over her husband Bjorn's private chat, as she does not have the secret blocks. She'll have to guess the secret blocks until she loses hope. However, Shor's algorithm exploits quantum superposition and entanglement to perform more computations at a given point in time, while using fewer qubits than bits a classical algorithm would need.
Big O is a measure of how increasing an input n scales the computational time of an algorithm. A classical computer would brute force solve an integer factorization problem in sub-exponential time, and the computational time explodes for higher n. However, Shor's algorithm for quantum computers works in sub-polynomial time. Simply put, it takes a shorter time. This makes the integer factorization problem of Dolly practical to solve using a quantum algorithm.
While quantum computers indeed demonstrate the potential to break encryption widely used in the modern day, they are still distant in terms of development for that to occur.
In addition, cryptography is not just a stagnant field. Methods of regulating quantum supremacy have been created in the form of algorithms that inhibit these computers from breaking into your personal data once they gain enough of a foothold to become the prominent computer.
Meanwhile, Dolly composes a song about auburn-haired Eileen taking back her man Björn to fundraise for a quantum computer to obtain back the key to his heart.